Today we are going to talk about CSI-13, and that is the topic for today's discussion is computer networking. So we are going to talk about the topic for today's discussion is IEEE standards. So let's talk about 802.3 cabling now. Now here is just like this. Now Ethernet is referred to as a cable now. So we use a different type of cables here. So let's take about what type of cabling we are using. When you design the local area network, we use different type of cables now. So one such cable is what we'll call them. Then we have a 10 base 5, 10 base 2, then 10 base T and 10 base F. These are basic specifications of your cable, and it is called the 10 base 5 is called thick coaxial, this is called thin coaxial cable, this is called two-state pair, and this is called fiber optics. And I will try to explain you at a later stage that what exactly we have. And the maximum size of a cable segment is what we'll call them 500 meter, then you have a 200 meter, then we have a 100 meter, and then you have a 2000 meter. Then nodes per segment, maximum nodes you can connect with this type of segment. So whenever you design a local area network, you must have understand the basic configurations now. So you must have how many nodes per segment, maximum node you can attach to this 100. If you have a more machine, you want to attach to this type of cable segment, then you have to have another type of segment, right? So before you design your local area network, you must understand the limitation of a cable. Otherwise what will happen is that the bandwidth will be reduced now, or your signal will be not signal will not be strong now. That is why when the telephone people put the cable two-state pair for sending the signal, they always after certain distance they have to boost this signal. They always put some booster in between, so the signal cannot be deteriorated further. Now same thing happens in computer network, that the whole bandwidth of a signal is also divided on dependent upon the what is the size of your cable length. Now, so according to the bandwidth, the size, the length of a cable is fixed now. If you go beyond that, then again you have to have another set of cable, and then only you can do it. So all these technical specifications must be clearly understood by all the designers now. So when we say the bandwidth is, we are trying to talk about the what we call them channel capacity. More bandwidth, more channel capacity. Less bandwidth, less capacity. How we can decide that how many bits per second? So the electrical characteristics of a channel is defined by bandwidth, that is the frequency range. But the channel capacity, that the how many bits per second, it is divided by bits per second. So BPS or MBPS or KBPS, these are the basic units you have to, or gigabits per second. These are the channel capacity. Now the question can be that how we relate, how we are able to find out that given the bandwidth of a particular channel, how you are able to decide what will be the channel capacity. Although we have not discussed this topic in our for BITS students, but just for your information, that there is two basic laws we have in computer network. In the computer network is basically two major topics we discuss in computer network. One is what we call them data communications, and second is called computer network. We are discussing the topic related to data is computer, what we call them network. But the data communications deals with, there we have two basic laws. One is what we call them Nyquist law, and second is called what we'll call them Shannon's law. So through this law we define what is the actual channel capacity of a particular, what is actual channel capacity of a particular channel, you can say. But these two laws are independent of any channel. They are not meant for coaxial cable or two-state pair or something like this. They are independent. They are mathematical laws. They are theoretical laws. But somehow you can find that they are nearest to the actual calculations now. And one such law is Nyquist law. We will not give you the formula, but basically Nyquist law says that if bandwidth is given, then you can easily calculate your channel capacity, and your channel capacity will be twice the bandwidth. For example, if I am talking about 500 megahertz channel capacity, then the 1000 Mbps data can be transmitted through Nyquist law, provided you have a binary encoding, means each signal will carry only one element, either 1 or 0. So it means the bandwidth can be increased not by changing the cable, but also by changing the different encoding techniques. So this is what another issue you have to understand very well. So Nyquist law is one such law. So but what we came to the conclusion that by increasing the bandwidth, I can increase my channel capacity, and according to this law, twice you can achieve if you have only binary encoding. Encoding means again what is my bit pattern for sending the signals now. Suppose that I am sending more than one bit in each signal element, then so many times I am increasing my channel capacity. But there is a limitation that you can send number of bits with particular signal element, because the receiver has to understand the complexity will be in the hardware design and so on. This is one issue you have to understand very well. The another law is what we'll call them. So when we study data encoding, we'll know that different way of encoding signal takes place now, but we are not going to talk about. The another important law is what we'll call them. The Shannon's law is basically they also calculate the channel capacity given the bandwidth of a channel, but they also consider noise factor. The Nyquist law always assumes that the channel is noiseless, whereas Shannon's law always consider the channel is always noisy, which is true now. So they consider the noise factor or some other factor they also consider before they transmit the data. So these are the basic issues you have to understand, the relationship between the channel capacity and what we'll call them the bandwidth now. Here there is another information which you have to understand is we have used called baseband and broadband. Baseband is used for digital signaling and broadband is used for analog signaling. This is what you have to understand. This is what the basic. So all the cable now exactly we can say when I write 10 base 5. What exactly we understand by 10 base 5, that is something you have to understand now. By 10 base 5 means, let's look at this slide. 10 base 5 means that it operates at 10 Mbps, right? And they use baseband signaling, digital signaling, and can support segment up to 500 meter. 5 stands for 500 meter. So what we have three type of informations built in. So all the cable will have this type of specification. So as a local area network designer, now each time you work with local area network, you must be aware of these basic concepts: 10 Mbps, baseband signaling, digital signaling, and 500 meters this length of a cable now. So and there is a limit that you can have a number of nodes within this 500. If you want to have more nodes, then you have to increase or you have to have another segment. Now you cannot extend it further, but you can have another segment of a 500 meters. So this way you have to understand the cabling mechanism now. So we have when we talk of 10 base 2, it means 10 Mbps baseband and 200 meter of cable length now. Now the cable length also decides, as I told you earlier, that cable length also decide the bandwidth. So depending upon bandwidth capacity, the cable length is selected now. So if you have again there is a relationship, you have bigger cable length, then the bandwidth will be smaller. So that way the issues have to be examined. Now then we have another type of cable. I will just simply read now. We have already explained now. So what with 10 base T, this is another type of cable. There is no cable at all, right? Here is basically, so in hub, that you have the various devices called hub, which is a full box of electronics. Adding or removing a station is simpler in this configuration. Is much more easier than the normal what we have discussing so far, and cable breaks can be easily detected with 10 base T type of cabling now. But disadvantage of 10 base T is that the maximum cable run from the hub is only 100 or 150 meters maximum if the high quality twisted pair are used. Also a large hub is more costly. So again 10 base T is again it is much more flexible than we are talking about 10 base 2 or 10 base 5, and in hub type of design we use a 10 base T, right? But again you have a certain drawback with this type. That in computer I am talking about a hub. In computers we are talk about number of hardware devices now. We have talk about different type of hardware devices. Hub is one, switches is another one, what we'll call them. The repeater is another one, then we have a bridge, we have a router, we have a gateway. So all these network devices which we have, just like in computer fundamentals, you have learned about registers, stacks, counter and so on. Same way in computer network, we come across with large set of devices. So this is one such device now. Now and what about the 10 base 5? So 10 base 5, so when we talk of this 10 base 2 or 10 base 5, basically we are talking about the coaxial cables now. Now use of fiber optics here is much more expensive due to cost of conductors and the terminators attached with this type of cabling technique, but excellent noise immunity. It basically gives you the noiseless type of environment compared to other cabling which we have, what we call them, they are more noise is much more than the fiber optics. So today fiber optics has become the dominant channel. They are used in different type of configurations. Now the another type of, see, normally you remember what for because it was not required to refer to your Shannon's law or the Nacus law into the discussion, but I referred with one intention, that you must understand that when I try to calculate the channel capacity, the channel capacity is not only dependent upon the bandwidth but also the encoding techniques. So normally by default we understand that is a binary encoding is going on, means each signal element will carry only one element. Now only one, each signal element will carry only one digit, either high or low. If you have 5 voltage above, or let's say around 3 voltage above, it will be interpreted as a 1, whereas below 3 voltage will be taking as a 0, and so on. But what happens sometimes you will see that in the local area network, in Ethernet type of technology, we use different type of Manchester encoding, not for carrying more signals each bell, no, but what we happen sometimes, normally what happens, the idle bit, if the sender is not sending any data, right, and the sender is sending some data, both are, if the one bit and the idle bit both are treated as a 1. So what will happen, that is very difficult sometimes for a receiver to understand whether sender is sending some idle bit or not sending anything, or sending some 1 bit. So basically to distinguish between the idle bit or the actual data bit or the control bit, end bit, start bit, they use different type of techniques, different type of encoding techniques, what they call the Manchester encoding, so that receiver and the sender should be fully synchronized. They must understand the semantics of the each bit transmission going on between the two devices without referring to any external clock. So the clock is built into the while transmission is going on, and this type of technique is called Manchester encoding. So in both we have two type of similar techniques called Manchester encoding and differential Manchester encoding. In both type of techniques we use this type of in local area network we use this two type of technique. Now what is Manchester encoding? But one thing is very much clear to you, that we try to differentiate between different type of bits, and sometimes that same bit can represent a different type of meaning. So one has to understand, one has to fully synchronize with the semantics of the transmission going on between the sender and the receiver. Let's look at the slides. I will just explain you this word once again, what exactly we mean by the Manchester encoding. Manchester encoding removes ambiguity in what type of ambiguity? In determining of a start, a stop and middle of each bit between a sender and a receiver without a reference to an external clock. Whereas a binary encoding, this is what I referred to when I was trying to calculate the channel capacity now. So now when I am trying to do this one, what we are trying to do now, when we have a in the binary encoding, what we have, the 0 bits, 0 volts for the 0 and the 5 volts for 1, right. So does not distinguish between idle senders and the 0 bits now. So this is basically to distinguish between these two concepts, the Manchester encoding is there. Now what exactly, how it happens now, what type of signal message A is built into this type of encoding, so that the receiver is able to stabilize itself or able to distinguish what is going on. Now how it works, how it is different, or rather how it is different from differential from the binary encoding. With Manchester encoding, each bit period, the time to complete this one, is divided into two equal intervals. Each bit period that is divided into two parts. First the half, a binary bit, like for example 1, binary 1 is sent by having the voltage set high during the first interval and low in the second one. So first half it will be high if 1 is going on, and second half it will be low in this one. A binary 0 is just the reverse, first low and then high. So this way, so see, when the data is going on, the receiver will always get to synchronize that, say the binary the two intervals are taking place. So again, this is a part of data. It is not a part of the ideal bit or not a part of any other type of bit sequences now. And there is right. So basically there is another scheme is there, differential Manchester encoding also. Now again, so what basically, let me just give more information about the Manchester encoding now. So what happens here is, just look at this, that each scheme ensures that every bit period has a transition in the middle, making it easy for a receiver to synchronize into the senders now. So they have a transitions now, right? So a disadvantage, now what you have, they will be getting synchronized properly, but the disadvantage of a Manchester encoding is that it requires twice as much bandwidth as encoding a straight binary encoding, because pulses are half the width. So the more transition is taking place, so more bandwidth will be required to send the data. But always data will be accurate. The receipt of data as the receiver will be as it is, without any ambiguity between the receiver and the senders and so on. Now this is all, and we have a similar techniques, what we call them differential Manchester encoding, but the commonality between these two are that they all have a transitions in between. Now this so far I have been explaining you the cabling mechanism, the encoding mechanism, the philosophy, the protocol, how it works, mostly hardware point of view. Now let's talk about, you know, that when we send data at a data link layer, they are always in certain type of format, and one such format is what we call them 802.3 format. So each protocol have own frame format. Let me talk about one such today, 802.3 frame format now. So when we send data, they always come into type of number of frames now. So frame has a start bit, frame has the end bit, frame has a control bit, frame has a data, and so on. So when I send email, when I do some FTP, when I do some telnet, we always do in terms of large, we always, the informations are always sent in terms of frames or packets, you can say now. That is why we call them packet switch network. Data is not transferred in one go, right? It always stored, divided into number of packets according to the size of the routers and bridges on the way, and stored for the stored temporarily and forwarded further if the line is free or there is no congestion at all. So each frame will have, apart from data, the number of other fields. Let me talk about one such frame format, what I will call them 802.3 frame format. So the first is called preamble. This is the first field of preamble. This is basically used for synchronization purpose, telling receiver, yes, now you have to get synchronized. Now the frame is going to start, but get ready to receive the data. Now that is something, right? So to generate certain type of pulses, certain type of bit patterns to inform the receiver that the transmission is about to start now, and the start of the frame. So basically for synchronizing purposes, speed and so on. The start of frame delimiter is 1 byte, means now the frame is going to start now. First one was for synchronization purpose. The second was just to tell that now the frame is going to start now. The third one is for destination and source address now. Now basically when you send your email, if I am sending, my address will be built into it. Whom I am sending, his address will be also will be there. So same way, how many, no, this is when you design any layer. Last time we have discussed, when you design any layer, you must decide what should be the address size of each layer now. Now here is, we have agreed now that in Ethernet technology or 802.3 frame format, the size of a packet, size of a frame, the address either for the source or for the destination is 2 or 6 bytes, or so maximum. Now it has been settled to 6 bytes. So either it will be 6 bytes or 2 bytes, but now it has been fixed to 6 bytes. So all the source and destination addresses are fixed to 6 bytes. Now the length of data field means how many bytes it will be, how many bytes are there into the data, that is decided by the 2 bytes fields now. and the size of the data, that is from 0 to 1500 bytes, right. The padding, suppose that sometimes there is a requirement at least so many byte size information must be there. If the information is not adequate enough, certain extra bits are added to it, and that is called padding, and so on. And then finally we have checksum now. Now checksum is basically the error correcting mechanism now. Now error correcting mechanism is basically that when you send your data, then what you have to do, when you send your data, then always some error correcting codes goes. Just like in ASCII coding system, the 1 bit is reserved for the control bit, 1 bit is reserved for the control bit, on for error correcting part of it. Only 7 bits are reserved for what we call them the actual data. With 7 bits you can have maximum 128 character representations, but with 1 bit you can have the whether the data which you have sent is a odd parity or the even parity. Same way, when you send a frame or packet, the error correcting code has to be designed, has to be built along with it, and there is a mechanism called CRC, cyclic redundancy check. So right, so this again 4 bytes are reserved for error correcting codes now. So this way whole frame is generated by the Ethernet or 802.3 format now. Now frame, I have already explained you about the preamble. Each frame starts with the preamble of 7 bytes, each containing the bit patterns of this type. The Manchester encoding of this pattern, what it does, it produces a 10 megahertz square wave for 5.6 microsecond to allow the receiver's clock to synchronize with the sender. So both, when we say preamble, is basically set of signal patterns is generated. A square wave is being generated, signal wave, and so that the receiver must get fully synchronized with the sender's clock and so on, so that the bit will be captured in its durations time itself. High order bit of, now what I remember we talked about the source address, we talked about destination's address, we talked about, and finally we agreed that 6 bytes are reserved for the destination address. Now you can ask, what are those bits are meant for? They have many meanings are there. It's not only one goes. See, high order bit of, like for example, high order bit of destination's address is a 0 for ordinary address. A high order bit of destination address is a 1 for a group address. Like if it's a 1 high order bit, the last one is 1 when I am talking, same message is going to group addressing. The address consisting of 1 bits is reserved for a broadcast, right? For a particular group, that bit has to be 1. But if I want to broadcast this message to all who are part of this local part of this computer network, then I have to broadcast this message, and what we call them, the all bits must be 1s. And then the bit 46 adjacent to the high order bit is used to distinguish local from the global addresses and so on. So basically when we are talking to, sometimes you see that, sometimes say that when you same mail you want to send set of people now, group of people. Sometimes you get certain garbage type of message at your email account, because some person through this broadcast type of message broadcasts all the same message to all. So in that case, particular bits patterns have to be generated, particular bits have to be set, whether it is for the individual person, whether it is for a group of people, or whether it is for the for all who are connected to this whole network, whether it's internet or whatever be. So that is the way the whole addressing takes place, right? So when you are examining any protocol, you are also examining the bit patterns of all the frame format now. What for they have been designed, how many bits for the data bit, how many bits for the padding, how many bits for the error correction, and definitely how many bits are for other purpose now. So this way we have to now the frame, now let's match. So this length field I told you earlier, the length field tells how many bytes are present in the data field. From a minimum of 0 to maximum itna bytes are allowed. If the data portion of frame is less than 46, which has to decide less than 46 byte which has to be there, the pad field is used to fill out the frame to the minimum size. So this is what we have about the 802.3 now. Now let's talk about 802.4, that is called token bus. Practically the token bus is, now let's talk about another such protocol. We have finished 802.3. In fact, I talked about another such protocols also for which there is no such a standard are there, but for example Aloha and slotted Aloha. Let's talk about another such protocol. This will be my last discussion, is about what we call them token bus, and the standard is 802.4. Physically, the token bus, let me see now, token bus is a linear bus, a linear or tree-shaped cable onto which the stations are attached, right? This way the whole cable is designed. A linear cable which number of nodes are attached to it. Logically, the stations are organized into a ring with each station known logically, not physically. How we organize all the stations in a different form, logical ring, because logically the stations are organized in a ring with each station knowing the address of the stations to its left and to its right. When the logical ring is initialized, the higher number of station, the higher numbered station which was initiated first or installed first, that may send first frame. After it is done, it passes permissions to its immediate neighbor by sending the neighbor to a special control frame called a token. So each one, now what we are coming to the conclusion here, just to try to see now how both the protocols are working. In CSMACD we observe that there you must have sensing of the carrier is this primary concern of any node which wants to send the data. Whereas in token bus or in token ring you will see that they must receive a token, a control token before they send the data. So that is something you have to understand. So first the highest frame or the highest numbered node will send the data, then after that the second numbered node will send the data and so on, right? Then what is the drawback now? The drawback with this type of token bus is very complex, right? You have to organize them. The adding stations on a fly is very difficult in the token bus type of systems now. But it's very easy with CSMACD type of thing. But CSMACD has another drawback. The major drawback with CSMACD is that they don't support you high priority. If there is no priority, then you can't handle a situations where data has certain information has to be solved or certain information has to be transmitted or processed on a different priority basis now. So it cannot be solved into the real time basis now. Now what happens? The real complexity lies here, because each stations having to maintain 10 different timers and more than 1 dozen internal state variables. So you have to maintain different type of timers. Unless you have a token, you can't do anything. Now now for the physical layer, 802.4 we are talking about. Now what they comprise of as a part of physical layer, I told you that each standard defines not only that layer which they belong to, that is the MAC layer, they also define certain things, certain functionality for the physical layer. Now for the physical layer, the token bus uses 75 ohm broadband coaxial cable for cable televisions. Now they use this is the specification. Both single and dual cable are allowed. 3 different analog modulation schemes are used, right? So they have a different type of techniques are used, different type of modulations techniques are used, right? And finally the speed achieved by 802.4 system is somehow a speed of 1.45 to 10 Mbps, and today we are talking about 100 Mbps Ethernet and so on. So it is much more higher. But advantage with 802.4 is a very the throughput is much more higher, number one, and number two is that it is able to support the real time processing which you have. And here is, you can just see the syntax, you can see now, just so the this format, this is a frame format of 802.4. you just see here is also we have destination address, we have a source address, we have a data byte result for the data bytes, we have a checksum. Checksum is again error correcting code, there is a end part of it, and there is a frame control, there is a start delimiter, this is a preamble. So just like so again, now your job will be to compare 802.3 frame format and 802.4 format now. So this way the whole structure is designed now. So here we have also around 6 bytes used for the source addresses, and again same way they work. They have also, to start with, you have to send the preamble bits, then you have to send the start and so on, and this way the whole. So here the basic difference between the 80.24 and 802.3 in terms of functioning is that token is the control which you have to receive first before sending the data. There is no such token as such. Anybody can send data at any time but before they have to sense the channel. That is so CS0 So 802.3 is much more distributed, much more flexible compared to 802.4, but their chances of collision is much more higher than the collisions in 802.4, because at a time only one token holder will be there in the net. But to get hold of that token, again it will get some time. So the at initial period the throughput is very low compared to what we'll call them in CSMA-CD, because they don't have to say, if very few stations are there, then the throughput will be very, very high. Here again you have to have some token before you send data to any other nodes. Now the so this is what, so you have to and here what you have to deal with many different type of problems, like what we'll call them token failure. What will happen if token has been failed? What you will do now? There is no such problem with CSMA-CD now. A station fails to, now what happened? Not only the token has failed, token is not visible now, is not circulating in the ring, but also it might happen the station fails to pass the token. I am holding the token that my station, that my node failed, my node is not able to work. Then again this will be a problem. Or suppose I am holding, right, again I am token holder, my system is not working, and then it might happen there are multiple tokens might be there in the, sometimes in the network. How to handle this type of situation? So they have a different type of problems. They have a different type of problems in the 802.4 than compared to this one. So anyway, we basically today as a part of IEEE standard, although I named number of standards belonging to IEEE series, but basically I discussed only two such standards, IEEE 802.3 and IEEE 802.4. But before that, I basically gave you various the problems related to this type of layer, or called problem related to the channel allocation in dynamic environment, where many nodes are trying to compete for it. So one has to resolve that who will be getting this channel, who will be getting access to this channel. And in this context, we discussed two types of channel allocations technique. One is IEEE standard series of mechanism, and the second one is what we call them static allocation, that is called FDM and TDM. And we try to compare the differences between the two, advantages between the two, and so on. With this, we are coming to an end. Next time again we will be talking about computer network with a different topic. Thank you very much.